Hello students. So now let us move on to the third module of Geotechnical Engineering II, which is on bearing capacity of shallow foundations. So the syllabus covers the bearing capacity of shallow foundation. In that you have ultimate, safe and allowable bearing capacity. What is the failure mechanism? What are the assumptions made to compute the bearing capacity? And you have only the Tersagi's bearing capacity theory in this subject, whereas there are other theories as well. Also, for various types of footing, how the equations are formulated. Derivations are not required because for exams most of the questions are problematic. You will be asked to solve the problems, so the concept as well as the equations are more important, as well as the assumptions. Such things will be asked. And then the various types of shear failure of soil, what are the factors which affect bearing capacity, and finally the settlement of the soil and how to modify the settlement, and all those aspects will be covered. So in Geotechnical Engineering 1, in the fourth module, we have discussed the shear strength of the soil, and in that I have also taught you that what is the shear failure of the soil. So in simple words, whenever an external force is applied on the soil, there is some mobilization of shear force. Okay, so if that mobilized shear resistance by the soil due to that applied load reaches the ultimate limit or the shear strength of the soil, then that soil fails. That is the what do you say, it is the universal law. That is whenever you are given any stress, there is a limit to which you can take the forces. Then anyway after that we fail. So that is happening in the case of soil as well. It will try to take all the force to it to the maximum limit, then it fails. So another thing that also you know, that the soil generally fails in shear. Okay, and why it fails in shear, that also if you have learned that part in Geotechnical Engineering 1, then you will know that, because the loading coming on the soil is actually the compressive loading by the footing. Here you can say strip footing, that is a compressive load coming onto the soil. But in soil the forces are transferred from grain to grain. You know that soil is having small grains, is it? Soil consists of water, voids, as well as small grains of the soil particles. So this stress is transferred through these grains. So naturally it is a kind of shear force which is applied on these soil grains, and that is why the soil is having that shear pattern, okay, shear failure pattern, because the force is transferred as grain to grain. It is not the, actually it is not the compressive force which is coming onto the soil. If you take an individual soil particle, it is actually the shear force. So that is how, that is why this angle of internal friction is very important. That is, the friction between the soil particles is very important in shear failures. Okay, so that is one type of failure, which is the shear failure. That means whenever an load is applied, if the mobilized shear resistance is higher than the shear strength of the soil, then it will fail. Then another type of failure is the settlement failure. So we have discussed in consolidation that how a soil is settling. That means settlement usually occurs in cohesive soils where there is a probability of consolidation. So there are different types of settlements, like a building is settling uniform, that is a uniform settlement. Here in the figure you can see this is a uniform settlement. And then there is a toppling settlement, a building is settling in the inclined direction. And then the last one, it is the differential settlement, which is the most dangerous settlement in fact, because a portion of the building is getting settled. This is because of the variability in the properties of soil. There are a lot of other criteria, because this happens in cohesive soils, which is a problematic soil. So this happens, this is a very critical failure, which is the differential settlement. So these are the two types of settlements in soil, that is the shear failure and the settlement failure. So we will discuss one by one. And now, so before moving on to the computation part, that how you are finding the bearing capacity of the soil, you need to understand some terminologies. So in this part, that is in this video, I will be mainly covering this terminologies, what all things you need to understand for formulating the bearing capacity or the bearing pressure of the soil. So here in this figure you can see here, this is the load coming from the building on the foundation. Now let us consider this as the footing base, and here the load coming onto it is Qn, that is the total weight of this column as well as the building which is transferred to this particular slab. So that is Qn. So let us consider this Qn as the net load coming on this footing. This is the footing here. And now what are the gross loads? That means if you are considering the base of the footing, at the soil underneath the base of the footing is under consideration, then what are the forces acting? You have this load from the building, definitely it is there, that is the net load. Then you have the weight of the footing, then you have the weight of the soil. So that is the gross load coming on the soil. Now you just bifurcate this, that is you have the net load Qn plus what is the weight of the soil? It is the area of the slab multiplied by the depth of the slab multiplied by the weight of the concrete. So you have this here, and also the weight of the soil, that is the area multiplied by the depth of foundation, depth to which the foundation is laid, minus the depth of the footing multiplied by the weight of the soil. So finally you have the gross bearing pressure. You multiply this total gross load by the area, you have this expression. Or if you want the net bearing pressure, then what you do is you need not consider the pressure applied by the soil, that is the stress applied by the soil, which is the weight of the soil into the depth of the footing. Okay, so that is the stress applied by the soil. So if you want to find the net bearing pressure, just you exclude this term gamma s into df to get the net bearing pressure. So overall you can say that net bearing pressure is the ultimate load coming onto this footing by the area. Okay, so now moving on to the terminologies in detail. So what is the ultimate bearing capacity? So let us read this carefully. Maximum gross intensity of loading at the base of the foundation that the soil can support without the risk of shear failure. So without failing, what is the maximum load which the soil underneath the base of the footing can take? That is the ultimate bearing capacity. What is the net ultimate bearing capacity? Maximum net intensity of loading at the base of the foundation that the soil can support, that is net force which the soil can bear without failing. So here just deduce the stress due to the soil or the weight of the soil multiplied by the depth of the footing here from the total ultimate bearing capacity. Now what is the net safe bearing capacity? It is nothing but the factored bearing capacity, that is you divide it with certain factor of safety, you get the safe bearing capacity. Always we have a factor of safety so that the design will be within the, there won't be any much failure in the design, or also to have certain to certain extent we can minimize the damage. So always whenever we construct any structure, there is always we keep a factor of safety. So here maximum net intensity of loading at the base of the foundation that the soil can safely support without the risk of the failure. So here we divide it with the factor of safety. What is the gross safe bearing capacity? It is the safe bearing capacity to which you add if the weight of the soil multiplied by the depth of footing, or to which you add the vertical stress of the soil, then it becomes the gross safe bearing capacity. So you have to understand each and every term. Why I am explaining these terms in detail? Because for exams it can be asked in any way. Questions can be asked in any way, like they may ask you to compute the gross safe bearing capacity, it may be asked as net safe bearing capacity. Any way questions can be asked. Also such terminology is very important if you also go for the competitive exams, because in that also for gate exams or any PSC exams of civil engineering, these terminologies are very important. So that is why I am explaining each and every terminology. Now moving on to the next last two terminologies. What is the safe bearing pressure or net safe settlement pressure? So safe bearing pressure is nothing but the intensity that a soil can take without undergoing settlement. And what is the allowable bearing pressure? Allowable bearing pressure is nothing but net intensity of loading that can be imposed on soil with no possibility of shear failure or the possibility of excessive settlement. So allowable bearing pressure is the smallest of the two values, that is the smallest of the net safe bearing capacity as well as the safe bearing pressure. So net safe bearing capacity is due to the shear failure criterion, which is formulated according to the shear failure criteria, and the safe bearing pressure is the settlement criteria. So whichever value is the smallest value, that will be considered as the allowable bearing pressure of the soil. That means if you are computing the net safe bearing capacity based on the shear failure criteria, and you are finding the safe bearing pressure based on the settlement criteria, so whichever value is smaller, that will be considered as the allowable bearing pressure of the soil. Now what are the various methods of determining bearing capacity? So moving on to the analytical methods, we have Terzaghis method, Mayhoff's method, Visis method, Hansen's method. There is also IS 6403 method. I will show you that method of IS code. It is not in your syllabus, but I will just show you how the method is used to find the bearing capacity. Then we have the Skempton's method. There are field methods like plate load test. Another testing is the standard penetration test and standard cone penetration test, dynamic cone penetration test, etc. So various tests. So these things later on after the end of the module, I will show how the field testing. I think plate load test and all, it's already there in the syllabus. So in the other modules, so we can cover that after in the forthcoming modules. So here we have only the Terzaghis method for your curriculum. So Terzaghi formulated this method in 1943, how you find the bearing capacity of the footing. So he formulated this equation for finding the bearing capacity based on various assumptions. And whoever formulated such bearing capacity theories, they had their own assumptions. So what Terzaghi did is, he assumed a footing. So before moving on to that, we will just roughly, I will just rush through the assumptions of Terzaghi. So what are the assumptions made by Terzaghi? So assume that the soil is homogeneous and isotropic, and the soil is a C5 soil, which is a cohesive soil. At the same time, it is a it has a 5 parameter. The shear strength of the soil is governed by Moore-Coulomb equation. Because it is a C5 soil, so it is shear strength is governed by the equation tau equal to C plus sigma tan phi. The base of the footing is assumed as rough. The foundation is laid at a shallow depth. That means the depth of the footing is always less than the width of the footing. That is called a shallow foundation. So what is a shallow foundation means? Whenever the depth of the foundation is less than the width of the foundation, then it is a shallow foundation. Another assumption, the footing is long, that means the L by B ratio is infinity because length is infinite. The shear strength of the soil above the base of the footing is neglected, that is soil above the base is replaced by uniform surcharge gamma df. That means I have shown you this footing here. So here in this footing you can see that if this is the footing, here we are considering this layer, that is the soil layer underneath this footing is under the shear. It is undergoing the shear failure, and we are not considering the soil around the footing. That is the assumption made by Terzaghi. Only the soil beneath the footing is undergoing the shear failure. So that is what he is saying, and that soil above the base is replaced by a surcharge. He assumed it as a surcharge of gamma df, that is he considered the total stress, vertical stress of the soil, vertical stress of the soil or a surcharge of gamma df. The load on the footing is vertical and is uniformly distributed. The soil fails in general shear failure mode. So shear failure modes we can discuss now, and Terzaghi assumed general shear failure mode. So whatever he assumed, this is how he he is assumed that the soil is failing in this pattern. This is the shear failure pattern of the soil. You can see here. You can see here a wedge and there is a spiral. This is a logarithmic spiral, and there again it is moving towards the end, that is towards this level of the base of the footing. It becomes a straight line, and he divided it into 3 zones. So zone 1 is the active zone, and this zone actually it forms a part of the footing. That means this fails along with the footing. That is how he has assumed. And zone 2 is the zone of radial shear zone. This zone undergoes the shear failure, and this is the Rankine's passive zone. He assumed it as 3 zones of failures, and then he formulated the equation. So here this particular zone is under the influence of this surcharge due to the soil above, this radial zone, which is called the passive zone. And the assumption, according to his assumption, we can see this is a retaining wall which is under passive pressure. That is how he has assumed it. If you take this face, then it is a retaining wall which is undergoing passive pressure. See this, you can see this wedge here is as a retaining wall which is undergoing passive pressure. So derivation part is not important, just know the concept that how the shear failure pattern is shown, or how he has assumed it, that the first one here is the zone, active zone, which behaves as a part of the footing, and these 2 zones are the radial shear zone, and this is the passive, Rankine's passive zones. And if this angle, he took this angle as the phi, that is the angle of internal friction of the soil, then these 2 angles he took it as 45 minus 5 by 2, and here also it is the same. It is actually the symmetry. You can see here whatever he has shown here, it is coming to this side also. It is symmetrical. So again in detail I will show you the shear failure pattern. So this is the wedge under the footing which behaves as a part of the footing, and this is the second zone which is the radial shear zone, and this is the passive zone. Now how he has formulated this equation, based on he solved this wedge, he made the free body diagram of this wedge, and he formulated this equation for the strip footing, and this is the equation which is formulated, that is Q ultimate equal to C NC plus Q NQ plus 0.5 gamma B N gamma. So this is the equation for strip footing formulated by Terzaghi. And he formulated the equation for the ultimate load, where C is the cohesion of the soil, Q is the effective overburden pressure, that is the weight of the soil multiplied by the depth of the footing. Here it is density of soil above footing into depth of the footing. Then gamma is the weight of the soil, B is the width of the footing, and this NC, NQ, and gamma are the bearing capacity factors which were formulated based on the angle of internal friction of the soil, that is which were formulated for every phi of the soil. So there is a table for finding the Terzaghi's bearing capacity factor. This I will explain in the next class, what is general shear failure and what is local shear failure. So for a given value of phi, what is the NC, NQ, and gamma? It is, you can compute directly from this table to find the ultimate load. So if you have all the terms and if you have this bearing capacity factors, you can find the bearing capacity for that strip footing using this equation. Now the remaining equations I will be dealing it with in the next class, and also in the next class we will go in depth what is general shear failure and what is local shear failure, and how the formulas are changing when the type of failure of the soil is also different. So that's all in this class. So here the most important aspects which are covered as far as exam point of view is you have to be very thorough with these terminologies, because in questions any type of capacity can be asked. So you must be thorough with the type of capacities, what are the terminologies, ultimate, whether it is net, whether it is net safe, etc. And another thing is how the shear failure pattern is assumed by Terzaghi to formulate the equation for bearing capacity, and also the assumptions of Terzaghi. So these parts are very important. and also this equation for a strip footing. Q ultimate is equal to C and C plus Q and Q plus 0.5 gamma B and gamma. So this is all about okay. So that's it for this class, and next things we will discuss in the next class. Okay.